integration by parts. So this is the first of the integration techniques that we learn in this section. Before we go into the nuts and bolts of this technique, there is an analogy between integration and differentiation, okay, or parallel techniques. We saw already one. We saw that the chain rule was corresponding to the substitution. So here are parallel techniques. On the left side we'll write differentiation. On the right side we'll write integration. So here's the one that we saw earlier. For differentiation we have a chain rule. This applied when the function was a composition. The equivalent technique when we did integration was the substitution technique. So basically, to undo the chain rule in differentiation, we integrate using substitution. Likewise, we have a technique that is parallel, so to speak, to the product rule of differentiation. And this technique is integration by part. Or by parts. Okay? So let's look at differentiation, or the product rule. Let's say you have a product of two functions, f times g, and you want to differentiate this d dx of f times g. Well, if you apply the product rule, then you have f prime times g plus f times g prime. Okay? Or if you like the uv notation, we can use u and v notation. If you have a product of u times v and you want to differentiate, it will be u prime v plus uv prime. Okay? Now, this is differentiation. If we want to undo what we just did, then we integrate. And as we integrate, if you look at the equation in f of g, so we undo differentiation, and we have now the product f times g. And now, since we have a sum on the right, the sum of the integral of a sum is sum of the integrals, so it will be the integral of f prime g dx plus the integral of f times g prime dx. Okay, so we basically undid the differentiation. Now let's say I want to solve for f, I want to evaluate the integral of f times g prime dx. So we rearrange and we get the integral of f times g prime dx equals to, this was on the right, so I'm solving for this term, so it will be f times g minus the integral of f prime g dx. Okay, and this is one variation of the integration by part, and indeed it's a theorem. Okay, now this is one way to write it. It is more convenient to use the uv term, and you'll see that it does make more sense. So to use the uv term, let's start with, let's u equal f, and specifically f of x in this case, because I didn't specify the variable as x except here dx. So dx was the differential of integration. But here I'm very specific. I'm saying v is a g of x, as u is f of x, and now I'm taking the differentials I differentiate, and du dx will be f prime, and the differential du will be f prime, and I'll drop the x here, and I'm going to say it will be f prime dx, like so. Likewise, differentiate v, you get dv dx equal g prime, and the differential dv equals g prime dx. Now, I'm looking at the terms in the box, and I see that I have f, which is u. So let's say if this is equation star, now I'll plug this in equation star, and I see that I have the integral. Instead of f, I'll have u. Instead of g prime dx, well, g prime dx is right here. It's dv. Okay. F times g is u times v, so that's okay, minus the integral. And here I have g times f prime dx. Okay, just rearrange that and write it as g times f prime dx. Well, g is v, and f prime dx is right here, sitting as du. And this is the more familiar form of the theorem of integration by part. And this is the rule, really. Before I give you the first example, I want to go ahead and review a list of, I think I have 10 basic integrals that we'll use not only in this particular section, or not only for this particular technique, but also for our subsequential techniques that we'll learn after integration by parts. So let's start with list of common integrals. Okay. The first and the most useful rule, probably the most common rule, is the power rule of integration. The integral of x to the power of n dx is, of course, 1 over n plus 1 times x to the n plus 1 plus the constant c. And then this rule applies for all value of n except -1, because x to the -1 is 1 over x, and for this we have a different rule coming up now. So when n equals -1, we have the integral of 1 over x dx, and here we have the natural log of the absolute value of x plus c. Now we have our favorite rule. The integral of e to the x dx is e to the x plus c. And something that we tend to ignore, the integral of a to the x dx. Well, the base is now is a generic value a. Well, we keep a at a positive value, and the result of this integral will be 1 over the natural log of a times a to the x plus c, and we'll keep, as I said, we'll keep it as a positive value. Okay, number 5, the next one. Now we go into trigonometry. The integral of sine of x dx is of course, what is it? Negative cosine. Okay, plus c, and the integral of cosine of x dx is the positive sine of x plus c. All right, so now we are looking at the integral of the secant squared of x dx and the integral of the cosecant squared of x dx. So what is the first one? Number 7. What is the number 8? Go ahead, say it aloud. Okay, the secant squared pairs up with the tangent, and the cosecant squared with the negative cotangent. Okay. Likewise, the last two, we have a product. We have the product of secant and tangent as our integrand. So the integral of the secant times the tangent, and number 10 will be the integral of the cosecant times the cotangent. Okay, so what is number 9? What function has a derivative that is secant times tangent? The secant. And what function has a derivative that is cosecant times the cotangent? Well, if number 9 was the secant, number 10 will be not the cosecant, but the negative cosecant. Okay, so we'll use these 10 integrals, and next we're going to run through a sequence of examples.